I'm going to start this video off by saying that NMR is not your friend. It never will be, and you don't need to trust it. You know, anytime you see NMR, you run. You run the other way, you scream, you tell everybody about it. NMR is coming. Don't trust it. Don't believe a word that it says, because NMR is just going to get trickier and trickier. And you're going to get to a point where you won't trust it. I mean, right now you might be feeling pretty good about yourself. Like, NMR, I got this stuff, right? I mean, the number of signals and the electronegativity values, I mean, how hard can this actually get? Well, you're getting ready to stumble in the world of integration and splitting. And we talked a little bit about splitting, but not much. And we're going to have to look at this integration first before we go into splitting. And you're going to start to see the complicated world of NMR open up petal by petal by petal. So integration, what exactly is this? I put on here, no, it's not calculus. So what does that actually mean, right? Well, let's talk about integration in terms of calculus. A lot of times when we talk about integrating, we've got some kind of shape that happens maybe in the math world and the calculus world. And integration is all about the area under the curve. It's typically how it's referred to in a math class. Area under the curve. Well, NMR has integration. And the reason that it does is because we have an NMR that looks like this, and then we get a signal that's coming from that NMR. But if we zoom in and if we look at that line, it's actually not a true line. It's actually more of an enlarged kind of view like this. It's more like a Gaussian curve in a way. Maybe not necessarily Gaussian, but we could see a very broad foot on this line that we've just been simply drawing as a line for convenience up to this point. All right, so for instance, if we go back and look at a previous problem, look at this in here, right? I mean, you can almost visually see that here now. These are not just simple little straight up lines that come up and come down. I mean, look at how wide this thing is at the bottom, especially with this one that happens right before a 2. So because of that, we can calculate the area under the curve, if you want to call it a curve. We can calculate the area under the curve of these NMR signals. So it's the same thing. We look at the signal that shows up with NMR. We look at the area that's under that NMR, and that area is something that's pretty important. And typically, most of the time, as the area increases under that signal, then the number of hydrogens increase as well. So it is proportionate. The area under the signal is proportional to the number of protons in the molecule that give rise to that signal. That is what integration is all about. All right. So typically in a NMR, we have a computer system that does quite a bit of this for us. We are not required to go in and integrate these by hand, for goodness sakes, right? So we're not going to go that far into calculus. But if we do see a signal that begins to show up, there could be a number that's associated with it. And that number is going to be in regards to an area, a possible area from that particular signal. All right. So just kind of jumping into the pool without being able to swim, I want you to take a look at what one of these examples might look like. And it looks like something like this. All right. So here's an NMR. Again, there's a signal here at 1, and it looks like a signal here at like 3.3-ish or right before 3.3-ish. I can't really zoom in and take a look at the footprint of each one of those spikes or those chemical shifts, but I know that we can integrate it. And the computer system will integrate it for us. And it will just give us these random little numbers, okay? So if I take a look at these numbers, here is a 7 and here is a 1.6. What on earth does that even mean? That's what integration is all about. So this 1.6 is going to be in reference to the distance between this line and this line. And the 7.0 is in reference to this line versus this line. All right, so if we go across, you're going to kind of see that this very first line that's drawn here is almost in regards to the TMS signal. That's where this line kind of starts, right? And then this particular line is going to start right at the top of that signal where it maxes out. So that's basically how they've drawn the horizontal lines on the NMR. I want you to think of this lowest one as the area that's at the top of the TMS, and then this next line will begin at the top of the lowest signal, and then that line will continue up until the max of the next highest signal. That is how those lines are generated. So they're letting you know that the distance here, I'm not even going to give it a unit, is a 1.6, and then this is a 7 in reference to that. So up here at the top, you see a ratio, and this ratio is 1.6 to 7. So normally what happens here is that we take the 1.6 and we take the 7 and we divide by the lowest number, whatever the lowest number is here. There's only 2 signals that we are referring to. If there was more than 2, there'll be more than 2 numbers. There'll be 3 and 4 and 5 and 6 numbers, and that's okay. But whatever is the lowest number here, you divide by that. You divide that number by all of them that show up in the NMR. So 1.6 divided by 1.6 is a 1, and 7 divided by 1.6, well, that's a 4.4. So the object here is to look at proton numbers. That's what HNMR is going to provide us. It is integration, it is area, higher the area, higher proton numbers, and we want to compare these two areas to each other in terms of a ratio and proportion. But we can't have 4.4 hydrogens. That doesn't make sense. You're either going to have one or all, right? So when I take the lowest number out of the ratio, the integral numbers that are here, when I take those values and divide by the smallest, I'll get this simplified ratio. It's still a ratio, though. And that simplified ratio could have these weird little decimals in them, and you can't have parts of a proton. You either have to have the whole thing or nothing. So at this point, we have to bring in a multiplier. We have to multiply it by something. We multiply it by 2, we multiply it by 3, we multiply it by 4, we multiply it by 5. I don't care what you multiply it by, but you're going to multiply by something in order to get something closer to a whole number. Now, it's not going to be perfect. It never will be perfect. We're okay with that. But this 4.4, it's not going to cut it. That's almost half. We've got to get something closer to a whole number that we can round off. So if I take this 1 and multiply it by a 2, I get 1 times 2 is 2. And if I take the 4.4 and multiply it by 2, I'm going to get 8.8. And 8.8 is close enough to a whole number. That kind of is a very good sign that this is going to just get rounded up to a 9 and we call it a day. So what these numbers are telling me, 1.6 and 7, is that if I do a little bit of math, basic math to this thing, if I do a little bit of basic math, the 1.6 and the 7, again, I'll do it again, 1.6 and a 7, I divide by the smaller number. 1.6 divided by 1.6 is a 1. A 7 divided by 1.6 is 4.4-ish. That is a simplified ratio at this point. And now it's my goal to get a whole number. So I'll multiply by 2. If I need to multiply by 3, I'll multiply by 3, but it doesn't make it any better. So 1 times 2 is a 2. And then 2 times 4.4 is 8.8. And that can be rounded off to a 9. So what this means is that this signal probably represents 2 hydrogens. And this signal probably represents 9 hydrogens. Okay, does that make sense? Yeah, it does. Here's why. This first signal that's coming from here, that first signal is the most shielded out of the bunch. The most shielded out of the bunch is the ones that's the furthest away from that bromine in the molecule, and they all are equivalent. Look at here. All 3 of those are the same. Ding dong! And I've got 3 from this one, and 3 from that one, and 3 from this one. What's 3 plus 3 plus 3? I hope that you would say 9. And we just worked that out with our little bit of math. The next signal is coming from the one that is the least shielded, the one that's the most positive, the one that aligns up strongest with the magnet, the one that requires more energy in order to flip because of that. And that is, ding dong, that one closest to the bromine. And look at how many hydrogens that thing has. It has 2. And based on our math, using the integral trace is what we call it, we can estimate the number of protons that's giving rise to that signal. And that's how we do it. So that is the world of integration. Okay? So look at your numbers. They will always be provided. These numbers will always be calculated by some type of software. They'll be given to you in example problems. Use those numbers, divide by the smallest. Almost think of empirical formula back in general chemistry. And then if you get a weird oddball one, then use a multiplier, a 2, a 3, a 4, or something in order to get it closer to a whole number that you can round up. If we're within like a 0.1 or 0.2, we're okay with that. We round it up, okay? Again, if you've got 3 signals, it's not a big deal. If you've got a number here, colon, a number there, colon, a number here, colon, you work it the same way, folks. There's no difference. You still divide each of these by the smallest out of the 3. You'll get new numbers that show up down here, just like we did in our previous example. Some of these might have some decimals. And if they have decimals, you bring in multipliers times 2, times 3, times 4, and you basically do the same thing that we did in the first example problem. No difference on how many that you have. If you've got 8 signals, you do it the same way. You take all 8 integration or integral trace numbers, and then you divide by the smallest, and then you multiply by something that gets them all close to a whole number, give or take a little bit. That's all that you have to do. Right? Now, the thing here that I want to mention is that I don't want this to actually fool you at times. The ratio does not tell you at all. The ratio does not tell you the number of absolute hydrogens. It tells you the relative number of them. That's what that is, okay? It just so happened to work out this way. We did a 2 here, and we did a 9 there, and it just so happens to have a 2 and a 9. But I want you to take a look at an example problem like this. This particular molecule to the left looks like it has 1 hydrogen here and 3 hydrogens there. So a ratio is a 1 to 3. Okay? On the molecule to the right-hand side, this molecule is clearly different. this CH3 group and that CH3 group, these are equivalent signals. So therefore, this is 6 hydrogens in total. And then that particular molecule or this atom has 2 protons on that carbon. And it's a 2 to 6 ratio. 2 total, 3 plus 3, 6 is here. But that 2 to 6 can be simplified, right? And that 2 to 6 can be simplified to 1 and 3. And that's what we're seeing here. 2 divided by 2 is 1. 6 divided by 2 is a 3. So if I do some work on integral trace and I end up with a ratio of 1 to 3, that could mean an actual 1 hydrogen and 3 hydrogens, just like it did in our previous example. That is what that meant. But I also have to keep in mind that is the basic ratio of them. And that 1 to 3 could also mean a 2 to 6, because that means 1 to 3 as well in the terms of ratio and proportion. And that's exactly what we have up here. We have 2 hydrogens versus the 6 hydrogens. It just so happens that that can be simplified down a little bit further. So these numbers that I get from the integral trace calculation, for instance here, we said 2 to 9, it could be a direct match, like it was in this example problem, on the number of hydrogens of each type. However, if the molecule's bigger than this 2 to 9 could also be a 4 and an 18. I just multiply each one of these by 2. Or it could be a 6 and 3 times 9 is a 27. 6 of one hydrogen, 27 of another. Or I can multiply by 4. 4 times 2 is 8. 4 times 9, 36. I could have 8 of one type of hydrogen and 36 of another type of hydrogen. That ratio is the base. It is the foundation of the different types of hydrogens that are in a molecule. And it will be a simplified version every time. The reason 2 to 9 worked out here, well, it just so happened to work out. It just so happened to match. And that's where the confusion happens. Most people think, when you do this calculation, that ratio should be identical to the number of hydrogens that are in the molecule. And there are times where it will not be a perfect match that way. And that is okay. We accept that fact, right? Okay, so let's take a look at problem 15. It concerns integration. It says, how would integration distinguish between the NMR and the following example problem? So I see very similar things in all of these molecules, right? The difference, though, is that on the first one I see 1 bromine, and then here I see 2 bromines, and then here I actually see 3 bromines. So I'm first going to talk about signals. We're going to ding-dong these molecules and see how many signals we're going to end up with. So that bromine is connected to ding-dong, and then that carbon, no protons. I can't ding-dong that one. And then this CH3 group is the same as that CH3 group, which is the same as that CH3 group. So ding-dong, only 1 time. And this is going to give us 2 signals. That's it. Let's take a look at this one in the middle. That bromine is on a CH2. Ding-dong. Carbon has nothing in the middle. That CH3 group is equivalent to that CH3 group. So ding-dong, only once. And yet again, we see 2 signals. And I think you know what's going to happen with the third one. Bromines attached to the CH2. Ding-dong. And then this bromine is attached to a CH2. That's equivalent to that one. The bromine up on top is attached to a CH2. That's equivalent to that one. They're all 3 equivalent over here. And then we have the CH3 group to the left. Ding dong! So in each one of these cases, we're going to get two signals. In addition to that, each one of these only has a bromine on it as far as an electronegative atom. There's not a mixture. They're just all bromines. So if I take a look at where the shifts are located, well, yeah, I'm going to get a shift, and that shift is going to be in regards to bromine, but that one has a bromine, and that one has a bromine, and that one has a bromine. It has more bromines than the other ones, but they have bromines, so therefore the location of the shift will be about the same. So that's going to be really hard for me to determine as far as different NMRs go. I can't use the total number of signals, and now I can't use where the signals are located because they're all bromine based, and they're all going to show up kind of in the same area if I'm not careful. There might be slight differences, but nothing major. So the next thing in line that we can use to our advantage in NMR is the integration of the molecules that are located here. So the integration of these compounds will be different. Let's find out how. Let's find out why. Let's find out how to calculate them. So you might be nervous. You might be wiping sweat beads off your forehead because you're thinking, math, I don't want to do math. I don't want to do calculus. I signed up for chemistry. I didn't sign up for mathematics. It's not going to be that bad, I promise. So it says, how would integration be used to determine the difference? Pretty easy. This signal has two hydrogens with it, so I can put a 2 here. And then these other carbons have protons that are all equivalent. How many equivalent protons do we have in total? So there's 3 from that one, and 3 from that one, and 3 from that one. So 3, 6, and 9. So a 2-to-9 ratio. Next one, we see a bromine that's there. That has a signal that's associated with it. There's 2 of them. And then here we see 2 different CH3 groups, but they are equivalent. They are the same. So I get 3 hydrogens from the first and 3 hydrogens from the second, which is a 2-to-6. Now I want to simplify this down because I can. And that's really what we have to do in the integration world. So is there a common denominator here? Is there a value that we can divide both of these numbers by to make them smaller? And the answer is, of course there is. So 2 divided by 2 is a 1, and 6 divided by 2 is going to be a 3. So this is a 2-to-9 ratio, and this is a 1-to-3 ratio. And then finally, this last one, well, we said that all 3 of these are identical signals compared to the other one. So there's one signal that's going to give me 3 hydrogens and another signal that's going to give me 1, 2, 3, 4, and 5, 6 hydrogens. Is there a number that we can divide each one of these by to make them smaller? And the answer, of course there is. So 3 divided by 3 is a 1, and 6 divided by 3 is a 2. And this is how integration will be able to help determine which of these NMR spectra will match to these compounds the best way. The first one will give me a 2-to-9 ratio. The second one will give me a 1-to-3 ratio. And the third one will be a 1-to-2 ratio. And those numbers that appear on the NMR will allow me to calculate the ratio and try to match it to one of these. And whichever one matches the best, that's probably the one that goes along with that NMR. Okay? All right, so now we're going to look at an example problem here. It's problem number 17 on the slide. And it says an HNMR is shown below. And it's one of these particular compounds, A, B, C, or D. And we've got to figure out which one of these compounds it might be. So I'm going to stop the video here. I'm going to let you attempt this on your own. And I want you to go back and I want you to take a look at maybe that table. That will help you quite a bit and help determine which one of these kind of matches the best. So in the first one for A, we have an alkyne group. In B, it's just random alkyl groups. In C, we've got chloro groups, and in D, we got bromo groups. So take a look at that table, see what that table tells you, and see if any of these kind of match the signals from up above, and which one of those structures will be kind of the best possible structure for you to pick and put your money on when you bet. All right. So the next video we'll pick up here. We'll answer problem 17 and give you a discussion on why the answer is what it is. And then we'll continue on with the next part of NMR.